Hello and welcome to lecture 8. So as you can see from the prior lecture, we were talking about the coupling. We talked about queues, we talked about this coupled interface, readily valid signaling, all that good stuff. Now we're going to use that abstraction to build up yet again more abstractions. In this case, arbitration. That is when you have multiple hardware resources needing accessing the same thing, how do you moderate that? That's arbitration. So there's a number of ways to deal with that. The most common way is something called an arbiter. We will get there in the second half of this lecture. So that'll, of course, in real time, be in 2 days. But in this initial starting point, we're going to talk about some preliminaries that we're going to use to get to that point. So how do we actually build an arbiter? How do we go about applying an arbiter with something called a crossbar, which is a pretty cool example of how to apply it. We're going to get there first by talking about some of these initial things, which are not only useful hardware components, but they also demonstrate more of this parameterized hardware generation technique we've been covering in this course. So, fire up the old notebook. Okay. Then, first off, one-hot encoding. This is a common pattern in hardware design where if you have n things, normally you can use log n bits to represent that value. However, for one-hot encoder, you have some number of wires and exactly one of them is on at a time, right? In other words, one is true, the rest are false. So kind of comparing, one-hot encoding versus, more conventional, binary encoding, this is going to be exponentially more wires, right? What could be done with 2 to the n one hot wires could be done with just n wires in regular encoding. So why are we doing this? We're doing this because having things one hot makes a lot of other logic building easier. And so for modest values of n, we often use a one hot encoding because it's easy to do things. And we see this very common pattern is we'll have some collection of objects in hardware, and we only want to modify one, select one, enable one, etc. So what are some examples of this? Imagine you're building a processor, and you have your register file. You have your future registers, for your ISA. When the instruction is trying to write to register, it's only writing to exactly one register, right? So you only want one register to get the right signal one. The rest are going to be zeros, right? Or inside of an SRAM memory, you're only going to be, writing one row. That's the word line, right? That's going to also have only one of those is true. So that's often referred to as a decoder in an SRAM, where somebody takes in the row number and then it turns on only that wire. And so something that's kind of arbitrary format. Why we're doing all this, like I said, it can make a lot of other logic easier. And best yet, if you're kind of deliberate in your design process, you can set it up such that you kind of go into this one-hot encoding and you stay in the one-hot encoding. So you aren't kind of paying the cost of converting in and out of it. You just kind of roll one-hot encoding throughout. And so yeah, it's going to be a lot of wires, but these wires aren't going very far. The CAD doesn't optimize that well, and it's actually very kind of distributed, very nice design. Um, so let's see how we actually go about implementing this. So let's say I want to implement my own one-hot encoder. That is, I want to take a number in binary and then turn it into a one-hot encoding, right? So you can kind of see how this comes together. Whatever my input width is, let's say it's 4. Uh, if I have 4 bits, that's going to represent from 0 to 15, right? 2 to the 4 minus 1. Uh, that's 16 things. It's actually going to need 16 wires to do that one hot, and that's what this is out with it. So you see already our input width and our output width are different things. Sure. We're going to go ahead for simplicity require our input width to be greater than 0. Yeah, that makes sense. All right. How did I choose to implement today? Today I chose to do this with recursion, right? So how does this work? You can see what we're going to do is we're going to kind of concatenate things together. So you look at the base case is when does this recursion end? Where is the called recursion here? So if the index I'm working with is less than the out width, great, or out width minus 1 technically, I will kind of keep recursively calling. Eventually, index will equal out width minus 1, in which case I do the base case and I'm done. What am I doing along the way? Along the way, what I'm doing I'm concatenating the result of this recursive function call with a comparison, right? In other words, hey, is the input equal to this index? So you think about this, right? If I have, let's say, a 4-bit input, 16 output wires, I'm basically making 16 comparators, right? Was the input 0? If so, this output wire is now 1. If it was the input 1, if so, now do this, right? And so the concatenation is basically just all these things coming together. So there's a lot of components for this. I'll go ahead and declare it. And now if I go to the next slide, I can go ahead and print it out. And for just 2 bits, it's not so crazy, right? You can basically see, oh, wait, um, for a 2-bit input, 2 to the 2 number of output bits, right? And so you can see it's okay, so 4 bits, right? You see how this all kind of comes together, right? So IO out uh, is a variety of things. Its least significant bit, this is the Verilog syntax for concatenation, is true if IO in is equal to 0. Otherwise, it's T4. What is T4? The concatenation of is it, equal to 1, or is it equal to 2, or this other thing. What is this other thing? If it's equal to 3. So it's a structure we were hoping for. It's a little bit of a verbose way of getting there. Um, Alternatively, if we actually want to go ahead and run this, uh, we see it behaves as expected. Now, do I have a diagram next slide? No, I don't. This works. Cool. Let's now, for curiosity's sake, great, that works. Oops, I didn't mean to go that far. I meant to go that, oops, just there. Like a lot of things in Chisel, there's a standard library version, right? So we can do that. Before we do that, I'm gonna go ahead and turn on this printf. With the printf turned on, the test case is now going to print stuff out when it runs. So that makes it a little bit more interesting. Yeah, so you can see, for example, input 0, 1, 2, or 3, and this is not printing the leading zeros in the output, but you can see how it gets turned into one hot encoding. So we kind of see how this gets turned out. Okay, 0 is the least significant bit, 1, 2, 3. Okay, but now I'm curious, how did the standard library choose to implement this? So we can find out. Let's use the standard library version. So you can see it's just you went to one hot. There's a helper for that. I can comment out my code. And so, yeah, this function here is not going to be called. Just going to attach that. Great. Standard library does this. How do I do it? Drum roll. Really clever, right? So if you're looking at this, you're like, gee, that's a lot simpler to you wrote, Professor. Yes, it is. So standard library is a lot more clever. Well, how does this work? It's a dynamic shift, right? In other words, whatever the input is, it's going to set a 1 to that. So if the input is 0, it's going to shift 1 over by 0 bits, so it's going to be the lowest bit, right? If its input is 1, it's going to shift over by 1. So they just use a dynamic shift. Now, you'd be right to say, wait a second, how expensive is dynamic shift? Actually, not that cheap, right? Think about dynamic shift. There's a lot of ways for hardware tools to do it. However, my design, we were talking 2 to the n comparators. So is dynamic shift cheaper than 2 to the n comparators? Probably. So I would trust the CAD tools with that. Yeah, so this is an example of a very different way of doing it. Why I did the convoluted way? I did the convoluted way for yet more experience doing uh, recursion, and hopefully it's a lesson that you know what, for standard library components, someone spent a lot of time thinking about those, and they're probably going to be more efficient, and you have to know why that's not going to be better for you. And so, okay, cool. Questions? Let's keep rolling. So that was one-on encoding, right? The idea of taking some sort of number and then turning into a bus of wires where exactly 1 bit of wire is true. Immediately following it up with a priority encoder, right? And the reason why is we'll see that both a priority encoder using one hot encoding space output, this is going to be a really helpful tool for us to build up our article for later in the lecture. But for now, let's talk about priority encoders. What they are is, given a collection of wires, it's going to tell us the index of least significant bit. Or you can imagine it being the most significant bit. In other words, given a bus of wires, I want to know the first location that's true from either direction, depending on how you're phrasing the problem. And there, ordering in the bits, we kind of think of as the priority, right? So it would be for most things, least significant or least to most, whatever it is that gives the notion of priority. We want to find that bit, right? This comes up a lot, right? So imagine inside of a processor, if you have a five-stage pipeline, classically like from 120, and let's say you're doing forwarding data, right, from different instructions, right? You have like a register two being written by one instruction and read by another instruction. So you have logic there to detect, oh yeah, I'm reading register two, and another instruction still in the pipeline is write register two. I should forward that value. Okay, well, what if there are two instructions in the pipeline writing register two, right? Which one should you take? You should take the newer one, right? Because you want to have the more fresh value of register two. And so there's a precedence there. That's the priority. Another scenario you might want is, for example, say you have a collection of components, right? And they can be full or empty, and you want to find the first free slot. The order may not matter so much, but you need to pick a slot in particular, and using priority is one way to kind of have a distinct answer. You have like four slots available, and you just got to pick one of them. Using priority code is a way to have a definite answer. Be harder to tell, you know what, do that thing, right? And so, once again, chisel provides logic for priority encoder. You can have priority encoder for one hot output with priority encoder 0h for one hot. Very commonly, use a priority encoder to select between things, so it even combines it together with a mux. So these are all, helpful things in the Chisel standard library. So go ahead and read, the Chisel docs, etc. Now, one common question comes up for a priority encoder is, okay, if I have multiple bits, so I have a multi-bit wire coming into a priority encoder, and at least one of those bits is true, I can find the index to the lowest or highest, whatever my rules are, according to the priority. However, if I have that bus of wires coming into my encoder, a bunch of these wires coming in, and they're all zero, what is the correct behavior? There's no universal standard across the universe for this. Um, and depending on the scenario, that can either be declared to be an invalid input. You've now violated the requirement that the inputs, there at least be one, the input be non-zero. Or depending on implementation, it may return the maximum index. So you can see it's kind of varies. So that's a scenario where if that occurs in your design, hopefully you aren't depending on the output of the encoder at that moment. Okay. So if you're to go ahead and build these, here are two ideas, right? Um, the first idea, although the wires look simple, there actually are AND gates kind of in here that, you can blame my notation. These are hand-drawn figures. Maybe it doesn't make quite so clear. So you can imagine, you know, uh, when for it should, bit zero be the one that's the, uh, so I'm going to phrase that. This product code, first of all, is using a one-hot output. We talked about a second ago what one-hot means. So if bit zero of the output is true, not only is that going to be the only bit that's true, it's also going to be saying, of the inputs, um, that bit was also true, right? So yeah, you can see that here. If the input in zero is true, then that one's going to be true. Now let's say that's not true. Then, and not in zero. Well, if in one is true, then guess what? Then in one is the one. So this notation here is concatenation, right? So basically, one bit at a time kind of feeding into this bus. So originally, by here it's n bits. Up here it's just one bit and kind of, slowly adding one bit on at a time. And you see this AND gate kind of grows arbitrarily, right? It could be up to here, it could be n minus one inputs. So we're basically saying, is this last bit true and everything else false? Then yeah, it's the one. So that precedence is kind of encoded by this AND gate growing in size. So that's one approach to solving this problem. Another approach you might take is with muxes, right? And say, you know what? Hey, if the lowest bit is true, that's one. So yeah, this is true, selects the one way, it's true. If it's false, then it depends on this cascade of muxes, right? So you kind of see that based on where they are in this cascade of muxes, you can kind of take precedence. That's that priority kind of pulling rank. There's two different topologies. And once again, I'm kind of showing this to give you more examples of thinking of a circuit These are parameterized, arbitrary topologies. I'm going to go ahead and try and write these in Chisel. So I'll write these in Chisel in the next slide. Before we do that, I'm going to pause for any questions on the structure or purpose so far. Okay, let's try these in Chisel. So you can see a few different ways of doing this, right? So we're doing both of these with recursion. We'll cover functional programming in future weeks. How can we go about doing this? Well, with gates is the one on the left from before. Uh, okay, so we go ahead and call the with gates recursive function. With gates calls itself, and eventually, this if condition is false and it stops calling itself. That's the base case. So, uh, what does it do? Well, you can see it concatenates the recursive call with whatever the current index is negated and the expression. So, what is the expression? The expression is originally one, so that's going to be true. Anything and with one is that thing. So, it kind of is initially a no-op, but Um, as this kind of builds up, you can kind of see that when we call recursively, we're going to keep passing things on. In other words, keep growing this. So originally, this is, in zero is the expression, then we pass it on negated, right? So not in zero and this, and then it's going to be not in one and kind of, so a builds up that sequence of ands for us. So yeah, that's going to, totally work. If I want to go ahead and look at the Verilog, we can do that. Um, so yeah, you can see, hey, if the lowest bit is true, we're done. If not, it's this combination, which is this one true? And oh, what is this? It's over here. The Verilog is hard to read very quickly, but conceptually it's there, right? Um, and if I wanted to test it out, we can. Before I do that, I'm gonna go turn the printf back on. I turn the printf off for printing the Verilog because it makes the Verilog very complicated for no reason. And we see how the priority encoder work. Well, the zero case is weird anyway, so we can forget that. But if one is true, we get one. If two is true, we get two. Now, if both one and zero and one are true, which one do we get? Well, the zero bit has higher priority, the zeroth location, so that one wins. Same thing, kind of counting up, right? Okay, these other two are both zero, so then finally that bit wins. However, if any other bits are on, they're going to take precedence, right? This is that priority encoding in practice. Cool. So that was doing the gates. Now, if I wanted to go ahead and do that with muxes. The mux one, maybe this is more clear, right? You kind of see, okay, as long as, we're going through the recursive steps, I build a mux, which, is based on that input coming in. If it's true, I'm going to give the output. In this case, we're kind of computing that literal on right here. Otherwise, it's going to be this recursive thing, building up this tree of muxes, right? Okay, let's go ahead and look at the Verilog for that, which, you know, sure, three muxes for the three levels checks out. Questions? Okay, well then, now of course we should figure out what is the Chisel Standard Library going to do. Anybody have a guess? I showed two ways of doing it, so it could be one of those two ways. It could be a third way. How would you do it? Can we dynamic shift our way out of this? They're going to do it with gates. Okay, gates. Let's see. I forget every year, so it's always fun for me to find out. Oh, it might be muxes. Let's double check and run to make sure I didn't refresh that. It's muxes. And let's say we were doubting of me. Let's go look at how they wrote their mux code. So we're doing priority encoder one hot. This code gets scary in a hurry because it's using some more advanced Scala features. But other than that, uh, so you're like, okay, priority encoder one hot. That sounds innocuous enough. What happens? Well, actually, under the hood, it's calling priority mux. So the generator implementer was clever. Um, Under the hood. And so what is priority mux? Well, it's going to take your one hot object from coding work here. So eventually find its way into the mux. If we go and look at that mux code, it's probably also be scary, but let's do it anyways. Priority mux. Um, this is the companion object, right? So where is the class? Oh, never mind. There is no class. This object has an apply method. It's returning something called sequtils. This is so deep inside the Chisel library. So there's something called sequtils, which is sort for a sequence. Basically, this is, you know, too hard to explain and also too hard for me to understand sometimes. Um, what is this like? This is just like when you're writing C++ code and you try and read the STL code for behind the scenes. It also is scary. We all understand what STL vector does. We don't always know how to internal the STL vector makes sense, right? This is kind of like that, where we've regularly gone someplace really deep into the library where, yeah, the code's a little scary. What does that mean for you as a person writing your own freaking, hardware? Uh, Manage complexity, right? Ideally, if you have complexity, it's contained inside your module and not exposed to users, right? So in our case, the mistake here wasn't that we used their code. The mistake was we decided to see how it worked, right? It did its job, right? It gave us, the functionality we wanted, right? The problem was that, we weren't poking around, right? So they actually encapsulated the complexity, boom, poking. Um, yeah, it's worth kind of being aware of that. My general advice is that for most of the time, for most hardware components, really trying to sweat every last object gate is not worth it. Get the thing working. That's kind of ad philosophy we covered in this course, right? Get your design working, get it passing test benches, get it running through the entire tool flow. And then, yeah, if you see, oh, wait, my design is too slow, too much area, too much power, go in and optimize that. And you can do that with profiling, right? Rather than just attacking random parts of your design for no reason, you can see from those tools, where is the time in the critical path going? Where is the area going? Where is the power going? And be more deliberate about that. So however you choose to write code, I recommend doing one that is you think the easiest to get to correct solution. So maybe you like gates, maybe you like muxes, maybe you find you're just more intuitive. I did them both today with recursion. You can imagine this with a for loop, with a var. You can imagine doing this with functional programming, which I haven't covered yet. There are choices. Yeah. Um, I don't know. In the shorthand, no. The short answer is no. Is there another version? But for example, if I just did this, right? If I just did the not one hotness, that's probably going to break some stuff, but also muxes still. So yeah, the muxes are commonly used. Muxes are one of these things where they can seem expensive at first glance in hardware, but they actually aren't the worst thing. The reason why is some very clever CAD tools can do logic simplification on muxes, so it looks like a bunch of muxes, a sequence, like I just showed you. They recognize this pattern and do something more clever. Um, Other times, there's some really simple hardware components to actually build muxes extremely cheaply if you're willing to do dynamic logic. So muxes aren't always the worst. If you're an FPGA person, maybe you've been trained to be afraid of muxes, and you should be, because yeah, in FPGAs, muxes are much more expensive than they are for ASIC, but I wouldn't drive off a cliff to avoid the muxes. Cool. Okay, I think we're about at a good stopping point. Yes, we are. Let's stop there. Okay, stay tuned for part two.